Hi, I'm Sara Blachman, and I'm going to be telling you about the phytoplankton models I've built. Phytoplankton is a fancy term for microalgae. Think of them as the tiny drifting plants of the sea. They are important because they form the base of aquatic food chains. Shellfish and other small animals feed on phytoplankton. These animals are then eaten by predators like the blue crab, which are in turn enjoyed by you and me. However, massive quantities of phytoplankton, known as algal blooms, can be harmful and are becoming more frequent in some coastal waters. Last month, a bloom of toxic phytoplankton made its way from the mouth of the York River just outside these walls, 30 miles upstream to West Point. Some types of phytoplankton are more likely than others to contribute to such harmful blooms. And certain environmental conditions, like high levels of nutrients and warm temperatures, have been found to favor harmful groups over beneficial ones. Which brings us to my thesis. I've created 4 mathematical models, each of a different phytoplankton group. Together, these models simulate the total daily abundance of phytoplankton in an estuary down in North Carolina. The groups, shown here in this box, were chosen based on their prominence in the estuary. The arrows connected to the box represent the mathematical equations I use in my model. If that sounds complicated, don't fret. These are the same types of equations you would use to calculate a loan from your bank. The green arrows pointing into the box represent the effects of light, nutrients, and temperature on the daily growth rates of each group. Light stimulates photosynthesis in phytoplankton just like in all plants. Nitrogen and phosphorus in the water act like fertilizer on land, accelerating growth up to a point. When it's cold, growth is slow, and it increases as water warms. But if it gets too hot, growth begins to slow again. The arrows pointing away from the box represent the loss of phytoplankton, as it is grazed upon by animals, flushed out of the estuary into the ocean, and as it sinks to the sediments where it decays. I am testing my model against real measurements from the estuary to ensure they are accurate. I will then use them to predict how each group responds to environmental changes. What happens if the temperature increases 2 or 5 degrees? Or if the amount of nitrogen entering the estuary is doubled or cut in half? Would we have more yummy phytoplankton, or would harmful groups benefit? My model will be used by environmental managers to answer these types of questions in order to predict how phytoplankton populations and therefore water quality could change in the future. Thank you.